Number one, what are the geographic, temporal, and operational characteristics of industrial process heat demand in the United States? And then two, what are the county by county opportunities to meet IPH demand with solar technologies? And this little figure on the right shows currently installed solar process heat installations in the US as of about 2019. There are a few more ongoing in California at the moment, but there's, as you could probably imagine, a lot more process heat demand, a lot more solar resources outside of those areas, and that's really what we wanted to uncover and to understand. So why do we care about industrial process heat? Well, industrial process heat is a major energy use in the United States. The industry sector as a whole is the second largest user of energy behind the transportation sector. Industrial process heat within industry is the majority of fuel energy use, equivalent to about 40% of energy use in the transportation sector and about 28% of residential and commercial buildings combined. And another notable aspect of industrial process heat is that the energy is provided by fuel combustion mostly, and most of those fuels are fossil fuels. So if industrial process heat is mostly powered by combustion fuels, why are we interested in solar? Well, the top portion of this figure shows the cumulative industrial process heat demand by temperature in the United States for 2014. And the little bottom part of this figure shows the solar supply temperatures for several different solar technologies. And as it so happens, a lot of our industrial process heat demand is below temperatures of about 300 degrees Celsius. And that matches pretty well with the provision temperatures from these different solar technologies. But temperature is only sort of one piece of the equation. We also need to know about temporal and geographic characteristics of industrial process heat demands. All right, so this little figure gives an overview of how we approach the problem. So our analysis framework and overall approach. What we did is to characterize the hourly industrial process heat loads and match them with the appropriate hourly supply of heat. So on the left-hand side of this little figure, we start with estimating the hourly county level fuel use for all these different industries. We then layer on information about technologies and their limitations, including their end-use efficiencies, to arrive at an estimate of the process heat demand. On the right-hand side of the figure is where we have our solar heat portion. So we start with geospatial and temporal solar resource modeling, and then arrive at an estimate of the process heat generated. And this little box here, that dashed line box in the middle where they intersect, is what we consider an opportunity for solar industrial process heat. We formally define that opportunity as the fraction of process heat demand that can be provided by solar technologies given available solar resources and land area. And this little table highlights some of the aspects of the scope, some of the things that we included and some of the things that we excluded from our analysis. I wanted to highlight a few of those on each column. So the first is that we only consider a county average solar resource. Additionally, we consider the county total land availability. What we exclude, relatedly, is a site level analysis of these different process heat demands. We exclude economic considerations, and we exclude emerging solar technologies. So why is this a study of note? Well, it's a key, albeit first step in exploring how solar IPH technologies could be relevant for U.S. industries. We expand the idea of solar for IPH to include PV-connected electro technologies. And because we are performing analysis at the county level, our results can be aggregated and used at the national, state, and local levels as well. And this is really just a first step in understanding a very complicated issue. And so we have made our data sets and calculation code publicly available for download. We've developed a little interactive results viewer. Here's a screenshot screenshot here over on the side. All of these resources are linked in this URL here at the bottom of the page. So you can go and download data, look at the web viewer, and learn more. All right, I wanted to switch gears and jump quickly into industrial process heat. One of the first jobs that the team had to tackle was improving the data disaggregation of existing industrial process heat data. Now, this table shows 4 key characteristics of data that we were interested in. So characteristics in terms of geographic, temporal, temperature, and process disaggregation. So essentially what the team did was take regional annual energy data and estimate hourly process heat demands, including some equipment characteristics. And this was the foundation of our analysis. We then moved on to identifying which technologies were included in the scope of our analysis. Here's an overview figure that you'll see again later in the presentation, but how this breaks down for these conventional industrial process heating technologies and applications. These break down into conventional boilers, combined heat and power, and other general direct process heating equipment. On the solar technology side, we have 3 different solar thermal technologies, as well as 4 different PV connected electro technologies. And this is the part of the presentation that I will pass over to Jingyi to talk more about these electro technologies, the analysis that we have done. And I will go ahead and Jingyi, I'll continue driving the presentation, and you can talk through the slides.
Hello, everyone. This is Jingyi Zhang from Northwestern University. I will mainly talk about the technical potential of electro technologies. In addition to modeling boilers and CHPs, electro technologies were selected based on 3 criteria we defined in our analysis. And the selected electro technologies are photovoltaic technologies plus ambient heat pumps, electric boilers, resistant heating, and waste heat recovery heat pumps. The selection was based on weighted scoring of technical potential to replace conventional technologies, data sufficiency, and also market growth rate. So here we can take a close look of how we select the electro technology based on the screening. We have 3 different criteria. The first criteria is technical potential for conventional fuel replacement. The second criteria is data availability, and the third one is market growth outlook. Each criteria is measured with score rubric and weighting factors. For technical potential for conventional fuel replacement, if this technical potential is greater or equal to 500 trillion BTU per year, then we give a score of 3. If the technical potential is between 100 to 500 trillion BTU per year, we give a score of 2. If the technical potential is less than 100 trillion BTU per year, we give a score of 1. The second criteria is data availability. We did literary review on case studies and engineering models. If there are sufficient case studies and engineering models, we will give a score of 3. If there are some, we will give a score of 2. And if there is only few case studies and engineering models, we give a score of 1. And for the market growth rate, this criteria was based on the 5-year growth rate reported from APRI's report from 2015 to 2020. If the market growth rate is greater than 10%, we give a score of 3. If the market growth rate is between 0 to 10%, we give a score of 2. If it's a negative growth rate, then we give a score of 1. And for these three different criteria, we think the technical potential for conventional fuel replacement is the most important one, and we give a weighted score of 2, and we give the other two criteria, data availability and market growth rate, weighting factor of 1, and then we calculate the overall score for each electrotechnology. And from this table, we can see the electric boiler, ambient heat pump, resistant heating and melting, and the waste heat recovery heat pumps have relatively high overall score, and we will talk about two of them in the following slides. The first electrotechnology I would like to talk about is the electric boiler. In this slide, it shows the technical potential of replacing conventional boilers with electric boilers. The technical potential was estimated by current fuel combustion of conventional boilers in different industries, boiler capacity distribution, and maximum electric boiler capacity. This result assumes a single boiler replacement with a maximum electric boiler of 119 million BTU per hour. This means one conventional boiler can be only replaced by one electric boiler, and the maximum capacity is about 190 million BTU per hour based on our literature review. And from our analysis, we know that the total fuel usage for conventional boiler is about 1,759 trillion BTU per year, and about 52% of this fuel combustion can be replaced by electric boiler. And the total technical potential for electric boiler is about 916 trillion BTU per year. And from this figure, we can see that food industry, paper manufacturing, petroleum refinery, and the chemical industries have relatively high technical potential for replacing conventional boilers with electric boilers. And this is mainly because they have relatively high fuel burning usage in the conventional boilers. So we are going to talk about the technical potential of waste heat recovery heat pumps in this slide. So the technical potential of waste heat recovery heat pumps, we noticed that there was some literature already talking about the technical potential of waste recovery heat pumps, but our analysis is different from theirs due to the two main points. The first one is we matched the heat sink with heat source by collecting case studies, and we also considered the waste heat that has already recovered in the system, and we calculated the waste heat recovery by this equation listed in the bottom. The waste recovery is equal to the input fuel from the process times the waste heat can be recovered from the process, and then times the waste heat not recovered fraction, which is obtained from the literature. And the output heat is calculated by the input work or heat times the coefficient of performance. And a more intuitive way to show this equation is the input work or heat is equal to the waste heat recovery divided by the coefficient of performance minus 1. And after our calculation, we see the input work and the heat is about 36 TWh, and the waste heat recovery is about 330 trillion BTU per year, and output heat is about 453 trillion BTU per year. And from this figure, we can see the food manufacturing, beverage, paper manufacturing, petroleum and co-products manufacturing, and the chemical manufacturing have relatively high technical potential of waste heat recovery heat pumps. And I think next part we'll talk about the solar generation part.
Thank you. First of all, I'll just say hi, just so that people see me. And I will also stop the video just to make sure the bandwidth is good. So I have the fortune of talking about solar resource and land in the US. So clearly, the United States has incredible solar resource all across the US, as shown in the two images. Those are looking at the global horizontal irradiance, GHI, and the DNI, the direct normal irradiance. As you can see, the range is huge for both GHI and DNI. For example, 1450 to 2740 for DNI. Now, that raises a really interesting point, which is, since there's so much of solar across the US, how then is it suitable for solar industrial process heat? So the first point is, because there is a significant solar resource, both for GHI and DNI, there is significant potential because, for example, with PV, the low cost of PV is actually making it possible for PV to be a heat generating technology. For CSP or solar thermal technologies, it's a known and established way of providing solar heat. And for example, if you look at the image on the bottom, the Southwest has been typical for CSP for electricity generation, but can actually be much more across the entire country because you need a lot less solar resource for heat generation than for electricity generation. When you look at it from the land availability perspective, what's really cool, and it kind of quantifies it later, is the land availability for solar industrial process heat in each state is typically much greater than the land needed to meet the entire state's demand. And actually, in some of the slides later, we'll show that, and it's really cool. What's important to mention is that the modeling criteria and a lot of the extra material is in the back of the presentation and also will be available later. Next slide, please. So again, as Colin was mentioning, there are technologies being looked at in this report and this work, and then the demand side. So I'm really keen to showcase the technology perspective and the supply side. So for example, we looked at 7 different technologies for being PV driven. They include flat plate collectors with water storage, parabolic trough collectors with oil, with and without storage, 6 hours of storage, linear Fresnel direct steam generation, and then PV-based heat technologies, which are AC-based, such as the heat pump and waste heat recovery heat pump, and DC-based, such as the electric boiler and resistance heater. Now, clearly, electric resistance heaters can reach very significant temperatures, but need to be proven at commercial scale. Next slide, please. So how did we do a lot of the modeling? The backbone has definitely been the use of the NREL system advisor modeling. The current version is 2020.11.29. And again, when you click on the link, it goes straight to it and you can download it. So we defined specific technology parameters for that technology package. For example, with the PV system, a 1.2 megawatt AC PV, which would produce enough for a which would be enough for a 1 megawatt DC system, right? And so we're producing that type of modular system for a state. Then using the renewable energy potential model, we actually did something really cool where we're taking that same technology package, running the SAM code for solar irradiance and the technology parameters, then doing it across the entire country 3,000 times, once for every county, and then figuring out how much heat is generated per county. Really cool stuff. Using our high performance computing and the REV model as well. For the PV and heat pump models, it is really good to say that we had collaborator Stephen Myers, and we've used and developed, he developed those models. So again, the hourly generation profiles from SAM, the system advisor model, we have then coupled that hourly PV generation to the heat pump model offline, so that you can lift the ambient air temperature and then store that heat in water and then dispatch it to that load that's being met. Again, there's a lot more detail in the back and also in the report. But next slide, please. And that's where that supply to demand, when you match that, you get into the opportunities, which Carrie will continue with. Thank you, Colin.
Okay, thanks, Parthiv. Hi, everyone. This is Carrie from Northwestern. And I'll start going through some of the results and pointing out the opportunities. So first, as mentioned earlier, we calculated a process level heat demand for each of the solar technology packages. And these results are shown in this chart. They're grouped by industrial subsector here. And again, this is based purely on the demand side analysis, so based on the technical characteristics of the solar technologies and what portion of heat demand they could meet. So the 3-digit codes on the x-axis represent the different industrial subsectors, and I've labeled a few of them above. So the highest process heat demands that solar technologies can meet are in the pulp and paper, refining, chemicals, and food subsectors. And all of these require a lot of low to medium temperature steam, which is why for some of the concentrating collectors, there's very high potential. Okay, so on this slide, we now show the solar heat potential, which now accounts for how much solar heat could be generated from our supply side modeling. So this potential is based on hourly calculations of solar fractions, which is the fraction of heat demand that solar can supply. And that was done for each county and totaled for all the subsectors in all the counties here. The technologies with the highest solar heat potential are represented, which is represented by the bars in this chart, are the concentrating collectors like linear Fresnel and the parabolic trough collectors with and without storage. The dots, which are shown by the second axis, represent the solar heat potential as a fraction of the total heat demand that was calculated for the technology. So for example, waste heat recovery heat pumps have a really high fraction of total heat demand, which means they were found to meet roughly 50% of the heat demand that they were theoretically capable of meeting, but their overall potential is quite low, whereas some of the solar thermal technologies, which have high potential, were found to only cover around 20% of their theoretical heat demand. Okay, looking at the same solar heat potential, but now in a few key subsectors individually, food, chemicals, pulp and paper, beverages, metals, and petroleum. So there's high potential in several of the subsectors for the parabolic trough cases again, which can achieve higher temperature heat than some of the other solar thermal technologies. But even flat plate collectors as a non-concentrating collector, so that these would be the dark blue bar on the far left, they can still provide a substantial amount of heat in the food, beverages, and chemical subsectors. And then even with PV plus resistance heating, which is the light medium orange bar, it has high potential in metals industries, for example. Okay, so of course, the temporal aspect of this analysis is very important since we're evaluating a renewable energy technology with relying on an intermittent source. So we constructed these county level maps showing for each county the frequency that solar heat can fully meet the process heat demand. And so this again was based on the calculated hourly solar fractions for each county, where a solar fraction of 1 or greater indicates that the solar heat is meeting demand 100% or more of that hour. So the maps on this slide show a few of the cases, and the colors of the different counties correspond to the percent of the year that solar fully meets the demand. The darker red indicates a higher percentage. And then lastly, the percentages amounts associated with the colors vary slightly by technology because some were able to meet demand more often during the year. So for example, on the top left, the flat plate collector case, FPC can meet demand for many counties around 70% of the year or more, whereas electric boilers just below are closer to meeting demand 30 to 40% of the year on average. For the parabolic truss cases on the right, there's a distinct variation in the southern, middle, and northern parts of the country, and this occurs because the PTC cases were modeled based on temperature limitations, and ambient temperature affects the supply of solar heat throughout the year. Another variable in our analysis was the way the solar systems were scaled. So we modeled 2 scenarios scaled to meet peak load in June and in December, so in a summer and a winter month. The winter-sized systems are generally larger because the solar radiance is less overall, requiring more collector or PV area for when the sun is available. So these 2 county maps show the FPC or flat plate collector case with summer and winter sizing. And here the color scales are set to be the same. So even with summer sizing on the left, FPC can meet demand about 90% of the year in a considerable number of counties. However, the difference is clear in that with winter sizing, more counties are meeting demand more often. And as Parsif mentioned, we also looked at the land use requirement for the different technologies. And so this chart here shows land use as a percentage of available land on the x-axis represented by the bars for both summer and winter sizing. And then also it shows with the dots the total load calculated for each of the technologies. So on average, for each technology overall, it ranges between about less than 1% to up to maybe close to 3% land use required out of the total available land. And it should be noted too that with winter sizing, more land is required. And then it's also expected that land use as a percent of available land here follows the total load, since the solar system was scaled to meet the peak demand in each county for either that summer or winter month. But it should be noted here that with the PV cases, there is a higher land requirement. And then below in the table, it shows the land use totals that were calculated for all counties for each of the technologies. And just as a comparison for the absolute numbers, the state of Connecticut, which is one of the smallest states, is about 14,000 square kilometers. And so you can see the most land required for the PTC cases around on the same scale as that. And finally, one of the last sets of results I'll show today is the amount of fuel savings we calculated for each technology. And so the amount of fuel displaced mirrors the solar heat potential. And so this bar chart breaks down the fuel displaced by fuel type, and that includes heavily used fossil fuels like natural gas, coal, diesel, and waste gases, as well as biomass. We also looked at how fuel savings vary by month, as shown in the 2 figures on the right. And these examples are for the linear Fresnel and PV plus resistance heating cases. So here you can see fuel savings increase in summer when solar availability is more abundant, and the share of fuels displaced varies by solar technology according to the process heat demand it could feasibly replace. So for example, with the linear Fresnel system, which generates steam, it's highly used steam is highly used in the pulp and paper industries that rely a lot on biomass as a heating source. So you can see a larger blue chunk that's displaced, which is biomass. Whereas with PV plus resistance heating, it saves a larger share of natural gas and coal, since its applications are mostly in the high temperature industries such as metals. We also calculated carbon dioxide emission savings based on these fuel savings and each fuel's emissions factors, and avoided emissions range from 5 to almost 140 million metric tons of CO2. And I think this is the last slide for me. So this is a summary comparing the technologies among each other based on two aspects. So how often during the year the solar technology can fully meet the heat demand, and that's shown on the x-axis, and for how many counties they can meet the heat demand at least half the time, and that's shown on the y-axis. So you can see here, oh, and one last thing here too is the size of the bubble corresponds to that technology's process heat demand. So the bigger the bubble, the more potential heat demand it could meet. And you can see that the FPC, the flat plate collector, and the parabolic trough collector with thermal energy storage, the two bubbles on the top right, they can meet demand most often and for the most counties. And so it's important to note for these two cases, they included some form of thermal energy storage. So this really shows the importance of storage, which is about to be discussed in the next section. And I'll pass it back to Colin now.
All right, thanks, Carrie. Great. So I'll just start to wrap things up here now. So just to recap, put together the first national level analysis of opportunities for solar for industrial process heat in the United States, conducted at the county level. These solar thermal and PV technologies that we evaluated can meet many temperature for industrial process heat, all told around a quarter of total industrial process heat demand in 2014. As Carrie mentioned before, there are a lot of counties, most of them, in fact, that have sufficient available land for these technologies, although it does matter in terms of the site-specific details. So I'll mention that a little more towards the end of this presentation. And then we did highlight a couple of key insights that we thought were important. So all of the contiguous states in the U.S. can readily benefit from solar heat technologies, meeting a large portion of their IPH demands. A second key insight was that it's possible for these solar technologies to reduce CO2 emissions by about 15%. And thermal energy storage really is the key success for these technologies. And just to drive this issue of storage home, here are two figures that show parabolic trough collectors with and without storage. So this is for a single county, Polk County, Iowa. The PTC without storage is on the left, PTC with storage is on the right. 6 hours thermal energy storage is part that I mentioned before. So you can see that just the 6 hours of storage not only increase sort of when the industrial process heat demands of that county are met, but also how much of those demands are met. And storage is really an important consideration for industry because industry has these large, very intensive, very energy intensive facilities that tend to need to run continuously. So they have high thermal energy demands in the middle of the night as well as in the middle of the day. So thermal energy storage is a key enabler of these technologies, related storage in general as well. So this research really is just the first step in understanding a very complicated issue. So some more work in these areas. We've identified four key areas for future research. So the first is this higher resolution analysis that I think we've been mentioning throughout the presentation today. And this is really about getting down to those location, facility-specific details to match supply and demand for industrial process heat. The second key area is, again, this issue of energy storage, so thermal energy storage as well as electric batteries for those PV-based systems. Third is an increased focus on integration efforts, so how to get these technologies actually integrated into the industrial facilities and their processes. And the last part to go along with this is supporting those facilities in evaluating these industrial process heat technologies. So getting information about solar thermal, PV, tide, electro technologies to the folks that are running these industrial facilities. So with that, that concludes the presentation portion of our webinar today. I think we've got just about 15 minutes or so for questions. I think go ahead and see what we have here. All right, team, I'm just going to go ahead and bring up some of the questions that Ryan has been collecting. So I see a question about the basis of storage capacity section. So what were those, I assume, what were the reasons for selecting those storage sizes? And maybe Partha, if you can talk just a little bit more about storage for these systems in general.
Sure. Thanks, Colin. So the storage sizing is obviously a difficult question, but it was based around providing sufficient hours, let's say 6 hours after sunlight hours. So let's say during the tail off of the evening or the start up in the morning. And it then gives us, that's what we were finding, that there is sufficient solar normally to drive the process in the day, and then you need some amount in the night. That's an optimization question, which is determined best at the site. But for the analysis, we went with a rough amount to cover about 25% extra after solar hours. Thanks.
All right. I see another question about storage, just to keep you on the line, Partha. Maybe some more detail about the specific storage technologies and media.
For the Indian market? Sorry, is that the question?
Oh, no, just in general, so that a little more detail about the specific thermal energy storage options that were selected.
Okay, sure.
Beyond the size.
Right. So, great question. That is based on two different storage media right now. So we went with water, typically for the less than 100 degrees Celsius situation, because it's the cheapest by far. And then for the higher temperature application, the PTC, the parabolic trough with storage, that's an oil-based system. Now, that may not be the most cheap or the most exactly suited, but there are other projects that myself and Colin and others are working on, which is looking specifically at storage options for more suited to industrial application. We were trying to highlight that storage would then increase the potential, and so significantly more work is needed on what types of storage and what sort of sizing is needed.
All right. Thanks, Partha. I see a question about, I think, our assumptions of completely meeting demand instead of sort of meeting partial demands. In terms of, I guess, something that maybe is more palatable economically for businesses to offset a portion of their industrial process heat demand in their fuel use versus completely replacing their existing conventional system. And so I think I will say that as a study in the vein of being a technical potential analysis, we wanted to push things as far as possible, to keep in line with those general assumptions. So we do have a companion analysis that was also produced with this funding that has recently been submitted to an academic journal for review, and there we look at sort of offsetting just a portion of process heat demand in two different industries. So there we have taken a much more techno-economic focus for analysis. So we do evaluate just a partial offset of process heat demand, and I think that is also something that is present in the marketplace as well. So industrial facilities using these solar technologies to offset a portion of their fuel combustion and fuel costs as well. And yes, Partha just answered a question in the chat about making the slides available. I don't know if we have recorded this presentation, but I believe if we have, we can make that available on our website as well. Let's see here. Not sure if there are any more questions coming through. Maybe I'll open it up to the rest of the project team to say anything that the presenters might have missed, or to share any additional information that you think the audience might find useful.
Colin, there's a great question on different load profiles for each subsector. Have we taken that into consideration, or do you want to just mention a little bit more about that?
No, I missed that. Yeah, I can go ahead and take that. So certainly, temporal aspect of IPH demand is something that basically there's really no good publicly available data source for it. So in order to get around that data limitation, the team went through a series of steps to essentially estimate load profiles from average weekly operating hour schedules. So we've been able to disaggregate and differentiate general load profiles based on industries, the general size of the industry, as well as some seasonal variations. And so again, I would say it's sort of part of this first step aspect of this study. It's certainly a lot more work could be and should be done on these load profiles, but it's a start in terms of just being able to differentiate in terms of those factors that I mentioned. So general industry, some seasonality, some size considerations as well.
Hey, Colin, it looks like there's another question here that didn't get an answer. It says, I'd be interested in how much expansion you would see if you considered solar plus wind plus TES hybrid systems to satisfy process heat loads. Thoughts on that?
Wow, that's an expansive question. I might also allow or ask any other team members to tackle that one. Anyone?
Colin?
Yeah, as Parthiv, I was just going to say, you've been working in the area of
I've been in the chat.
These hybrid systems.
It's a very good question. We have not included, not in this analysis, but perhaps in other analysis, we are looking at the interconnection or that potential between heat and also electricity. So exactly as you're suggesting, the person who suggested that, on PV connected heat technologies and wind connected heat technologies. We haven't actually gone down that analysis pathway yet. But thank you for that suggestion. We are thinking about how to do that. It's a tough one. I was also going to say, Colin, there seems to be a question on that slide 29, which I may not have answered.
Yes, was that about the meeting the full demand?
Yeah, exactly.
Yep. Just a question about future research directions for the work. So, I mean, I think certainly there's a lot of room to go down this route of higher resolution analysis and looking at location specific details in terms of the supply and demand sides of the equation. So something that we weren't able to incorporate into this national scale study was looking at specifically citing a solar field and looking at heat transport to a facility. So those types of location specific considerations are, I think, certainly ripe for analysis. If any, I'll put out a call for other team members as well to chime in with additional research ideas that weren't captured in this very brief overview slide here. Anything that folks thought is a natural next step for this work?
Yeah, I'll chime in. I know we talked on the last bullet point about the facility decision support. We talked a lot about making like a user tool for maybe industry representatives to input some information about their specific site and comparing different solar heat technologies based on certain characteristics and what amount of fuel savings they could achieve or how much it would offset their demand. So that seemed like a really interesting potential area for future research that would also work with partnering with the facilities that actually would use these technologies.
This is Eric Matsonet. I would also say one of the needs we noticed in the research is really understanding some of the co-benefits that come along with with solar industrial process heat technologies, reductions in floor area, reductions in abatement costs, and so forth. So as we think about future research on the techno-economic side, understanding those co-benefits, which could be an important part of the value proposition, is a really big research need as well.
Great. Thank you, Eric and Carrie. Maybe we'll take one last question here. Maybe combine some questions about comparison with the United States versus other countries in the world, and maybe give some specific examples of facilities that are using these technologies now. So I think I'll go ahead and take the first part of that question. I think our results are pretty consistent with what other folks have found in other regions of the world in terms of just the industries that these technologies make sense for, and some of the limitations as well. I know both Parthiv and Carrie have looked at what's happening in real life with these technologies and with facilities adopting them. I don't know if either of you would like to end with a couple of quick highlights of some interesting real world applications of these technologies. Maybe we'll call the day after that.
I mean, I can start. In our initial review for this project, we looked at existing facilities around the world that have installed solar industrial process heating, and then also a focus in the U.S. And we were only able to find about maybe 15 or so projects in the U.S. So the ones in our country that are doing it are mostly concentrated in the food and beverages industries. And a lot are in the Southwest, but there are actually some that are in northern states as well. There was a brewery in Wisconsin that was using flat plate collectors, and a lot of times these flat plate collectors, or even sometimes concentrating collectors, are used for cleaning or washing or other just kind of general process heating or steam type systems. So yeah, I'd say I think that's also on par with some of the studies I've read in Europe too, about the food and beverage being the first types of industries that these could be adopted. But yeah, we hope to think that, yeah, there's a lot of process heat demand in other industrial subsectors too. So hopefully we point out that maybe these could be used beyond just those two industries.
And I'll close with, we focused mainly on lower temperature, so lower to mid, so 400 degrees Celsius and lower. We have some, of course, analysis on the high temperature activities, but as Colin was highlighting earlier, the majority of the heat demands in the US can be met fairly easily. And so that's a lot of extra work in the future on much higher temperature activities. Colin, any last thoughts?
I think everything's been covered well. So I just take this opportunity to thank everyone for joining us today, and go ahead and ask additional questions. I'll put my email address up again. Can funnel questions to the folks who can best answer them. So once again, thank you all for joining today, and take care.